So here we are with chapter 4, the molecular view of reactions in aqueous solutions. Up till now we've done stoichiometry, we've looked at limiting reagent um, and percent yield, and we've had test 1. So this would be information for test 2 or exam 2. All right, so in this chapter we're going to look at how we describe solutions. We'll look at both the qualitative and the quantitative. Of course, the focus will be on quantitative. We'll distinguish between electrolytes and non-electrolytes. We'll look at how we balance molecular ionic and net ionic equations. That's going to be one of the big components of the next couple chapters that are popping up, are the net ionic equations. We'll learn to identify acids and bases, and we'll learn how to name them based on their formulas. And then we'll look at metathesis reactions as they're used to plan a chemical synthesis. And then we'll look at how to use molarity calculations. And then we're going to finish this off with titrations and chemical analysis. So we start off with the importance of water. Whenever we're doing chemistry, you don't see too many solids get mixed together and have a reaction happen. Typically we have to be in the right medium for that to work, and that's where water comes in. So one of the most common compounds on Earth is water. It dissolves many different substances, right? 60% of the human body or more is water. Some distinct properties of water would be that it can dissolve ionic compounds, and of course that's going to allow acid and base reactions to occur, and one of the products there will be water. So in essence, the reason why solutions become important to us in chemistry is it gives us the medium to allow these pieces to react. So reactions occur in solution. In fact, if I take the solid salts, a lot of times they won't react. They need to be put into solutions so that the ions can move around. So the reactants need to come into physical contact with each other. And as solids, that's not able to happen, right? So we can make that happen best with either gas or liquid phases, right? And of course that makes sense. We've looked at solids versus liquids versus gases. We know that we get better movement whenever we're in liquids and gases. In fact, solid, they only have a vibrational component. There is no actual movement. Now, if we cut back a little bit further, I believe it was chapter 1 even, when we talked about matter, we're here we want to be in solutions. And solutions means, by definition, we have a homogeneous mixture, right? That means we have 2 or more components that are mixed freely to the point that we can't tell that it's actually a solution, right? Everything should look exactly the same and be consistent from point to point. So the molecules or ions then are completely intermingled, right? And of course that means we have to have at least 2 substances. So we have to have 2, and in our cases, typically it's going to be 2 ionic compounds. So some definitions that you'll hear used, we talk a lot about solvents. And solvent is the medium that dissolves the solute, right? So solvent does the dissolving. Solutes are the dissolved. The component present in the largest amount. So if I take 2 liquids and I mix them together, sometimes it can be confusing which one was dissolving and which one was the dissolved. Well, in that case, for instance, if we take an alcohol and water mixture, the one that's in greater quantity is the solvent. The one that's in the smaller quantity would be the solute, right? Now that means for both our solvent and our solute, it could be a gas, a liquid, or a solid. Now again, we'll be working mostly with aqueous solutions where water is going to be our solvent, right? So we're going to have a liquid as our solvent, and typically it's going to be solids that are going to be the dissolved, which means they'll be the solutes. Now, the solute by definition is the substance being dissolved. Typically your solution is named based upon the solute. So for instance, if we had a copper chloride solution, that means that the copper chloride is the solute and the solution is probably aqueous. It can be a gas. For instance, you can have CO2 in the soda pop and the water, right? That's the fizz. You could have a liquid where we look at ethylene glycol that's in antifreeze. So it's ethylene glycol and water. Or it could even be a solid where we have sugar and syrup, okay? So don't get hung up on physical state. Now, obviously in our course, all of our applications are typically going to be a solid dissolved in a liquid, and the liquid is typically going to be water. But when it comes to the definitions of things, remember that's not how it has to be, okay? All right, so iodine molecules and ethanol. So again, we don't have to use water as our solvent. We could use something like ethanol. So here you can see a crystal of the solute is placed in the solvent. So there, right there is our iodine crystal. We have the clear alcohol solution. And then as that solid breaks apart, what we see is the intermingling of those different components. And so the iodine starts to diffuse across all of the alcohol. All right, in a cup of coffee that has milk and sugar in it, which are the solutes and which are or is the solvent? So your solutes are caffeine, sugar, and milk proteins, where the solvent is water. The solute is water, and the solvents are caffeine, sugar, and milk proteins. Or solutes could be sugar and milk proteins, and the solvents are water and caffeine. And then, of course, the solute milk protein only, solvent water and milk. And hopefully you selected A. All right, so solutions. We can characterize solutions, and the way we best characterize them is typically by concentration. Okay. Now, when we're looking at concentrations, there are several ways to report concentrations. One way is to do the solute to solvent ratio, where we take the grams of solute over the grams of solvent, or the grams of solute over the grams of solution. We could look at percent composition, concentration, where we take the grams of solute over 100 grams of solution. So we call those percent solutions. We can do these several ways, as we'll see. So what is the percent concentration by mass, there's the key, by mass, of NaCl in a 556 grams of solution that contains 23 grams of sodium chloride? There's your pause. So just like before. Hopefully you came up with E. Oh, they didn't show us their work. So let's look at the work here. So what we're going to do is take the 23 grams. We're going to divide that by 556 grams. And then we're going to multiply that by 100%. And that's how we should have gotten the 4.14. All right, a typical blood glucose level in 90 milligrams per deciliter. What is the percent concentration by mass of glucose in blood, assuming a density for blood of 1.06 grams per milliliter? All right, so that should be 0.0849%. And so this time we're going to take that 0.09 grams, right? So we're going to convert our milligrams. 1, 2, 3. So that's how we got 0.09 grams of glucose over 0.1 liter. That's the deciliter. 0.1 liter of blood. So we're going to get rid of liters of blood and put that in milliliters, right? Because we want the percent in grams per milliliter. So we'll get that switched to milliliters. 1 milliliter blood over 1.06 grams of blood. So now we have 8.49 times 10 to the 4 grams per gram of blood. And then, of course, we're going to multiply that by 100%. That's going to make that drop down to -1, or excuse me, -2. And then we'll move that over 2 places, 1, 2. And so we'll get 0.0849. All right. So relative concentration, if we look at a dilute solution, we have a small solute to solvent ratio, for instance, like something like eye drops. We could have a concentrated solution. That means we have a lot of solute to solvent ratio, something like pickle brine, where all the salt is dissolved. A dilute solution contains less solute per unit volume than more concentrated solutions. Right? So dilute and concentrated are relative terms. So if we're doing math, then obviously these two terms are meaningless, right? Because we're going to want to know how many moles are in that solution, and we're going to get to that. Right here, we're just looking at, well, if I buy concentrated acid, it's going to be this molar or this percentage. And if I'm using a dilute solution, then obviously I've diluted it down, so I've put more solvent in. All right, so concentration then, the first thing we look at is solubility. Solubility, grams of solute needed to make a saturated solution over 100 grams of solvent. This is temperature dependent. So as I heat it up, would I expect to be able to get more solid in solution or less? And hopefully you said more, right? So if you've ever wondered how grandma makes that super sweet tea, it's because she's adding that sugar when that solution is still warm. We can form what's called a saturated solution. So this is a solution in which no more solute can be dissolved at that given temperature. So we're going to maximize how much sugar we can put in the iced tea, right? So we want to do that when the iced tea is warm. And if you've ever ordered a glass of iced tea out at a restaurant and they bring you unsweetened iced tea and then they bring you sweeteners, you know you can put like 3 bags of sugar into that iced tea, and at the bottom you'll have a layer of sugar. And that's because you have saturated the solution. It can hold no more. An unsaturated solution would be one that's not holding the maximum amount. So, and that term holding, what I mean is dissolved, right? So if I have a solution, it can dissolve or hold so much solute, right? And so if it's a saturated solution, we're saying it can't hold any more solute. It's completely full. It's saturated. If it's unsaturated, that means I can put more sugar in. So again, you start at the restaurant with that glass of unsweetened iced tea, and now they bring you the sweetener, and you only add a half a bag of sugar in, and you can watch it all dissolve. And that means you've got an unsaturated solution. It's able to dissolve more solute. Some solubilities of some common substances for sodium chloride. We can look this up in the tables. In fact, you probably had the opportunity in the lab to see that I pulled down a big book to look up some stuff, and that book is called the CRC of Chemistry and Physics. It's got a bunch of constants in it, a bunch of different numbers in it, and these are some of the numbers I would find in that book. I don't expect you guys to memorize these numbers, okay? If you need to know these numbers, they will be provided for you in the problem or a source for you to get them. You don't have to memorize these. So sodium chloride, common table salt, about 35.7 grams at 0 degrees C. And of course, that's per 100 grams of water, right? So this is a percentage. It can hold about 35%. And then 39.1 if I heat it up. So you can see we get a pretty relatively good sized increase there. For sodium hydroxide, though, look at that increase. We went from 42 to 347. That's a huge magnification because of heat. On the other hand, we can have something like calcium carbonate, and here we have 0.0015, so it's not really soluble at all. And notice they didn't even give us the second temperature, and that's because as we heat this one up, what happens is the CO3 actually breaks down and becomes carbon dioxide. So it's like a plop plop fizz fizz almost. Okay, so, and again, this is all stuff I would look up in that CRC book. I wouldn't expect you to know these things. And again, if you need them, they'll be part of the question. So when we look at concentrations, we've seen saturated and we've seen unsaturated. We also have supersaturated. Now, supersaturated is exactly like it sounds. It's holding more than it actually can. And again, this is grandma sweet tea right here. So grandma sweet tea, we take advantage of this. She's going to heat that tea up and then put the sugar in so that she supersaturates the solution. All right, so it contains more solute than required for saturation at a given temperature. We can form this by careful cooling of saturated solutions. Now, typically they're unstable. And of course, if I cool it down enough, it'll crystallize. Right? And if you've ever made rock candy at home, this is a method to make rock candy is the same thing. So we'll take water, we'll heat that water up, and we'll start adding the bag of sugar until we can get as much sugar in until it looks like a syrup almost. Excuse me. And then you take some fibrous material or some wooden material. You need something with some fiber on the microscopic level, and you put that down into the water, and then you just let it cool down. And as it cools down, the sugar will naturally crystallize on those fibers, and that's where we make rock candy. Now, when we have solutions and we start playing with temperatures, we can get what's called a precipitate. And so by definition, then a precipitate is a solid product that forms when a reaction is carried out in solutions and one product has low solubility. So in other words, now I'm going to take two things that are normally soluble, they're going to mix together, and they're going to form one thing that's not soluble. And that one thing that's not soluble will then what we call drop out of solution. So dropping out means it is the precipitate. Okay, so whatever material drops out of the solution or becomes a solid, and we say drop out because if you look at the solution in the beaker, you see all the solid drop to the bottom, and that's where that term comes from. So a precipitate drops out of solution because it's insoluble in that solution, right? So we have an insoluble product. It naturally separates out of solution. So now what we could do, if it was an actual synthesis style reaction and we wanted to look at yield, we could then capture that with filtration. So here's the idea. We're going to mix two things together. So we have lead nitrate and potassium iodide. We'll mix those two together and we're going to make lead iodide, which notice it's a solid. Okay, and as a solid, we're going to see that precipitate out. And there it is. We can see a yellow solid form. So we took these two clear solutions, added them together, and we get a yellow solid that'll form out of that. Okay, it's pretty neat stuff. All right, so what is the precipitate in the following reaction? So we're going to take silver nitrate, aqueous, AQ, plus ammonium carbonate, aqueous, produces ammonium nitrate, aqueous, and silver carbonate, solid. So which one is the precipitate? Or last option would be there is no precipitate. Give you a pause and hopefully you'll say silver carbonate. We can tell because of the solid. Okay, it is that straightforward. Now remember, I hinted in the last chapter that eventually you will be predicting the products. So how will you know? Well, when we get there, you'll see I'm going to give you some solubility rules. And so we're going to learn to use those solubility rules to predict what products will be soluble and which products will be insoluble. And that will lead us into our net ionic equations, which at the beginning of this session I told you would be one of the key components of the chapter. All right, so let's look at electrolytes then. So electrolytes and aqueous solutions. If we have ions present, what happens is I can run a circuit across this, hook it up to a light bulb with a battery, and if we have ions present, that charge will carry through the solution as part of the circuit and light up the light bulb. If it's a molecular compound, then it won't, right? The circuit will be stopped right there. There's no connection there. Okay, so sugar and water are both molecular and will not pass a charge. Now I know you've been told ever since you're a little child, probably to stay out of the water during a lightning storm. All right, now that can really mess with us here in chemistry because what I need you to know is water is not a conductor. Water is not a conductor. Now the reason why you can't be in water during a lightning storm is because you are not water. You basically mess up the water from being a conductor and turn it into an ionic solution. Okay, so keep that in mind. Water, pure water, is not a conductor. Okay, only when we put an ionic solution in there or something that's giving off ions will it become a conductor and allow that circuit to be completed. So ionic compounds then will conduct electricity, molecular compounds will not. Why? Well, let's look at this. Water molecules arrange themselves around ions and remove them from the lattice. So now what we have are a bunch of charged particles floating around in water. And this could be a tough concept to wrap your head around. If it's not, that's great, because if you can take this thinking through with you, then you'll make a lot of sense out of reactions. So remember, to get things to react, we got to get them moving. And so what happens here is the water dissolves these particles, pulls each one off. So when we take solid sodium chloride, what it actually breaks into are sodium ions in water and chloride ions in water. Now each one of these ions will have a degree of water around them. Now remember, water is a polar solvent. So if I'm looking at HOH, we're going to find that this is a bent molecule. It's got a couple of lone pair of electrons up here on the oxygen, and it's going to produce an overall moment that goes like that. And so up here, this is going to be partially positive, and this is going to be partially negative. And so we don't need to know a whole lot about electricity here, but we do know that charge flows, right? And so these electrons are flowing. Oh, I think I messed that up too. This is the positive end down here. Whoops. That's the negative end here. So scratch that and rewind it. Put that back in. Partially positive is down here with the hydrogens. Partially negative is up there with the electrons. Made a little mistake there. Make note of that. Okay, and that's going to give us our flow. We know the electrons are going to go to the oxygen, and we're going to study this in more detail in a few more chapters, right? But because we have that polarity, if we have a positive particle, then the oxygen's electronegativity and that negative partial charge that's going on with the water will surround that positive charge. And we'll see just the opposite happening with the chloride. The chloride took that electron from the sodium and is now partially negative. And of course, that means the partially positive side of hydrogens will surround themselves around that ion. We call this process dissociation. Okay, so electrolytes dissociate. Non-electrolytes do not. And that's what's going to be the why. Okay? The salts will break apart into ions when they dissolve. So if sodium chloride dissolves, it becomes sodium and chloride ions. They're separated ions. We call them hydrated, and they will conduct electricity. Now, be careful with your polyatomic ions. The polyatomic piece will remain intact. In other words, the nitrate of NO3 does not break apart, but it's still ionic and carries a charge. So here's potassium iodate, and here we have the potassium, K+. The iodate stays as a unit, IO3 minus 1. Okay, now it still has a charge. It can still conduct electricity, but the IO3 part is going to be molecular. Now for molecular compounds in water, something like sugar, we still get a dissolution going on, right? So when molecules dissolve in water, the solute particles are surrounded by the water. So the whole sugar molecule gets surrounded by water, not parts of it. So not an ionic piece of it. The whole molecule simply gets surrounded. The molecule itself does not dissociate. Now, electrical conductivity is what's leading to these terms electrolyte. Okay? So electrolytes are solutes that yield electrically conducting solutions. So if I dissolve that solute into the solution, the overall solution will conduct electricity. Now, there are varying degrees of that dissociation. And so if I have a strong electrolyte, then that means it's going to dissociate at 100%. Anything less is not a strong electrolyte. So when we say it's a strong acid, what we're saying is it dissociates completely. So in chemistry, when we say strong electrolyte, strong acid, strong base, that means it's completely dissociating. That's going to make our calculations a lot simpler. If it's a weak electrolyte, or a weak acid, or a weak base, it actually complicates the math. We'll still be able to do it, and there's some tricks, but it's not as straightforward. Now, if we have a strong electrolyte, that means it's going to yield the aqueous solution that conducts the electricity. So we're going to have a good electrical conduction here. So for instance, if I use something like sodium chloride, potassium nitrate, these are strong ionic compounds, strong electrolytes, they completely dissolve. And so we can actually see this factor when we look at the light bulb and the conductivity tubes. So if I put potassium nitrate solution in and I hook the battery up and I get that circuit to go, we'll get a bright light. Okay, we'll get a very bright light. If we use a strong acid or a strong base, again, we'll see a bright light. Now, if it's a non-electrolyte, the aqueous solution that doesn't conduct electricity, so the molecules will remain intact in solution, things like sugar and alcohol. And then, of course, if we put that in the conductivity tube, there'll be no light, right? No light whatsoever. All right. So how many ions form on the dissociation of sodium phosphate? How many ions form? A little play on words here, right? So you might be tempted to say 2, but realistically we make 3 sodiums and 1 phosphate. That gives us 4. Okay, tricky, tricky. Let's try again. How many ions form on the dissociation of aluminum sulfate? Hopefully, fool me once, shame on you. Fool me twice, shame on me. This time, I'm sure you said, whoa, 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 there's 2 aluminums, 3 sulfates, total of 5, right? All right, so pay attention to how many electrolytes we're making. So we've seen a strong electrolyte. We know that's going to completely dissociate. We have a non-electrolyte. That means it's not going to dissociate. Everybody else is in the middle, right? Everybody else is either going to make it from 1% to 99%. So 0% non-electrolyte, 100% strong electrolyte. What do we do for 1 through 99? We call them weak electrolytes, right? So they have a weak electrolyte. So when dissolved in water, only a small percentage of the molecules will ionize. So some of them will, some of them won't, and that means we have all three things in solution. Common examples of are weak acids and bases, and so acetic acid, you had a good whiff of that in lab. Acetic acid is a weak electrolyte. Okay, so it does conduct electricity, but weakly. And so remember I talked about the conductivity tube with the light bulb. We saw no light, we saw bright light, and now we're going to see dim light. Okay, and so here, if we take HCl, we put that in solution. This is a strong acid, bright light. Over here we have ammonia. It's molecular, doesn't break apart, no light. And then finally, we take acetic acid, weak electrolyte, we get some light. Okay, some, not sun. So we get some light, small amount. Now, what's really interesting though is a picture's worth 1,000 words. Here we see that all the particles dissociated. We end up with water surrounding the oxygen and the hydrogen. So we have them all separated out. Here, notice we have 3 different particles going on, right? We're going to have some of the full molecule untouched. We have some of the anion, and then we're going to have some of the cation around. So we're going to have the one, and just in case you're wondering, that's the hydrogen that's going to dissociate. So that hydrogen comes off. These hydrogens all stay on the molecule. The acetate will flow around in solution along with the acetic acid, along with the H+. And so you get everything in there. Okay? Now, dissociation reactions then are ionic compounds that dissolve to form hydrated ions. And hydrated simply means we're going to surround them by water molecules. Now, in chemical equations, the hydrated ion will be indicated by the AQ. Ions are going to be written separately. So in other words, KBr is a solid. We'll go to K plus surrounded by water, plus Br minus surrounded by water. If we take a solid like magnesium bicarbonate, here we see the magnesium surrounded by water, 2 bicarbonates surrounded by water. All right, let's complete this learning check, and this has been a long segment, so we'll knock off after this. Learning check. Write the equations that illustrate the dissociation of the following salts. So I'm going to take sodium phosphate, and I'm going to break it apart by dissociation with water. What will the products be? You can pause here if you need to. 3Na plus aqueous plus PO4 minus 3 aqueous. So notice what happens when we do dissociation. Our subscript for our ions becomes our coefficient. Okay. Now remember, this is a polyatomic, so that 4 stays intact with the oxygen. So we don't have 4 written as a coefficient out here. Let's give it another try. Here's aluminum sulfate. We're going to go ahead and give a dissociation to that. There was your pause. You're going to make 2 aluminum 3 pluses. And this time, notice we have the 3 on the outside of the parenthesis for the sulfate, which means we will have 3 sulfates. How about calcium chloride? And hopefully you're getting the hang of this and you've got calcium plus 2 aqueous and then 2 chlorides. One last one, we have calcium permanganate. And hopefully you've got calcium and 2 permanganates. All right, so again, we'll stop here. And the next thing we'll start to do is look at reactions with these guys. All right, so stay tuned for segment number 2.